know about the regulation, just generally? What's the hallmark of this combined regulation? It is reciprocal. And it's regulated then reciprocally at this main, it's not the first irreversible, it's the second, isn't it, of glycolysis, phosphofructokinase, going that way, and then through gluconeogenesis, it's the one, because in glycolysis we're adding another phosphate, in gluconeogenesis we're removing the other phosphate. So in one it's a kinase, in the other it's a phosphatase. Okay, and so what is this regulation covalent? Is there a kinase? Is there a phosphofructokinase kinase? It's allosteric only, no covalent. So you know, in that first fluffy part we're introduced, there's covalent regulation, allosteric. In this case, purely allosteric, no covalent modification to reciprocally regulate glycolysis and gluconeogenesis. So this reciprocal regulation is affected then by a same overlapping subset of small molecule effectors which reflect the energy state of the cell, which makes sense. So if you have a lot of ATP, is phosphofructokinase active? It inhibits it. And that's unusual because that's actually the substrate too. So it's fructose 6-phosphate and ATP. ATP is going to donate its gamma phosphoryl group, and you're going to have 1,6. So you're going to have this biphosphorylated fructose. It's a substrate, but it's also an allosteric effector and a negative one. So it binds at another site, not the active site, and inhibits. So what do you think ATP then does to the reciprocally regulated? It's going to activate, right? So you have, I believe that's right. See, because we have AMP then as well. Okay, so AMP is going to activate glycolysis, phosphofructokinase, and I believe somebody flipped to the. Are you there, sir, for gluconeogenesis? It inhibits. And then what's the other one that's shared? Is it citrate? Citrate. So if you got a lot of citrate, you don't need glycolysis to be going. And then the other one is this funny. You know, we touched on it more deeply in this integration of metabolism. It's where you have a fructose form that has two phosphates, but the phosphate is in the 2 position. So, you know, when glucose is phosphorylated, it's glucose 6-phosphate isomerized to fructose 6-phosphate. Then we need to add another phosphate to this hexose because we're going to whack it in half and make 2 3-carbon sugars that are then going to isomerize to the same thing and go through glycolysis. So it's a symmetrical. They're at the ends. But the cell makes this regulator, this 2,6. So there's phosphofructokinase, which puts on the 1 phosphoryl group. There's a phosphofructokinase 2 enzyme that puts it on at the 2 position. It's kind of fortunate. And this is not a side product that feeds back into glycolysis. It's not. It's purely a regulator. And if you look at those slides, the slide that I added in the lecture, the concentrations of this regulator are 1,000-fold less than the fructose 6-phosphate. So it's not a substrate. It's just a regulator that's going to work on the enzymes, which are catalytic. They're there in catalytic amounts. It's regulators in catalytic amounts. And it can actually be, there's some mention there about hormonal regulation of its levels. Glucagon is going to reduce its levels. Insulin actually is going to raise it. So that's a hormonal control of the levels of a small molecule regulator that's not a product like ATP. So it's not actually in the pathway. So
I just went in that a bit just so that this 2,6-biphosphate doesn't bewilder you. Does everybody kind of have that now? Yeah, so because it's kind of strange. Like, is that an enzyme or what is that?
She says hormonally regulated by glucagon to decrease the production of.
It lowers the levels. Yeah. Okay. So, yeah, I think that's worth it. That could be on the boards. I think it's a very important regulation. So, okay, so that's glycolysis, gluconeogenesis. I think that's, we talked about beta oxidation, fatty acid biosynthesis, pentose phosphate pathway.
TCA.
Oh, TCA, thank you, Kwame. So, yeah, so TCA cycle. So what did we learn before? It's at the bottom of that slide. So how is the TCA cycle regulated? Is it regulated, or are these, what kind of enzymes? Yeah, dehydrogenases, right? These two dehydrogenases, those are the key regulatory steps. Are they regulated through phosphorylation? No. Allosterically? Yes. Feedback inhibition, right? It's ATP and NADH. You make a lot of that, you feed back, you slow down the citric acid cycle. So that's what we learned before. How is the citric acid cycle regulated? And along with pyruvate dehydrogenase, right? The entry point, same type of regulation. Okay, there's yet another level of regulation, this respiratory control business. So in this case, it's not the level of ATP that's feeding back, it's the level of what? ADP. So do you have ADP? And the reason why is you have this kind of backlog of electrons. They don't have anywhere to go unless you have ADP in the ATP synthase. So unless the protons can flow back through and that synthase can spin, and apparently it can only spin if the ADP is there, then everything comes to a halt. So the electrons stop flowing through the carriers in the membrane. They can't be deposited in the membrane by NADH or FADH2. So then those are reduced. So then what happens to the dehydrogenases? They stop. There's no substrate because those are the substrates. So the products feed back and inhibit allosterically those dehydrogenases, but then as well, if there's no ADP, so if the energy charge is high, which is the same thing, high ATP, high NADH, then there's no flow of electrons. And so that's the link between oxidative phosphorylation and the citric acid cycle. So that's respiratory control. Okay, now Kwame, are we out of, where are we now?
Yep.
Yeah, and so, we saw that before. It's hard, I hate to even go there. So glycogen phosphorylase, covalent regulation and allosteric, reciprocal regulation of breakdown and synthesis, another case of reciprocal regulation. I think that's deep enough for this. Okay, what else? Oh, yeah. So these were kind of arbitrary because remember I pointed out we saw that oxaloacetate seems to be kind of a key intermediate, but these are junctions, I guess. So just look through those and I mean we know this quite well. Glucose 6, it's not glucose, but glucose 6-phosphate, right? It's the junction to get to these different pathways in carbohydrate metabolism. And then pyruvate, we certainly understand pyruvate to lactate. So